Cordacity is still a release candidate. All of the code samples that we're going to see are based on working and tested code. We are aiming to get a stable release shipped before the end of the year. So, Cordacity is an open source toolchain designed to simplify the development process and foster incredible developer experiences with Corda. My name is Matt Layton. I'm the technical lead for the blockchain and DLT team at TradeIX. I've been with TradeIX now for almost 3 years, 2 of which have been focused purely on developing with Corda. And prior to that, I was a .NET developer for several years, and that time in the .NET space has had some influence over some of the features that you'll see in Cordacity. So currently, we've split this up into 3 separate APIs. We have Koto, which is a Kotlin framework, Cord, which is a Corda framework, and Concerto, which is a framework for building business networks on Corda and having a level of interoperability between those business networks. And that's just a very high-level overview of all of the features that are in each of those frameworks. So we're going to start by having a look at Koto, which is a framework designed to simplify and empower Kotlin development. We can start by looking at the validation API. So here we have a typical example of a DTO, and this is something that you would probably find in one of the outer layers of your application, say, for example, in a web API. And this has been annotated to provide validation requirements. There are some problems with this approach. First of all, you have explicitly tightly coupled dependencies, because wherever you require these annotations, you also require the dependency that is providing them. So if, for whatever reason, you needed to validate something at a more central part of your application, then you have dependencies baked into the core of your application, bleeding their way out into everything else. And this becomes something that's very difficult to change if you ever want to change those dependencies. This is also violating the single responsibility principle, because now this object has 2 reasons to change. It needs to change if you need to change the data requirements, and it needs to change if you need to change the validation requirements. This is also violating the dependency inversion principle, because your DTO is now dependent on your validation API rather than an instance of your validation API being dependent on an instance of your DTO. You're also limited to using constant values. As you can see there from the min annotation, you've got a constant value. You can't use any instance values. It's hard to validate with context. So as an example, if we were issuing obligations from Europe, we might want to accept currencies, which would be euro or maybe the Scandinavian currencies. But in the UK, we might only want to accept euros or pounds. So it's hard to do that with annotations. It's hard to validate things that aren't properties, so for example, function returns. So really, this doesn't offer a complete or unified validation solution. All our DTO should look like is that. This is clean, simple, maintainable, and expresses intent. And notice here that we've also introduced nullable types. As much as Kotlin's non-nullable type system is a really cool thing and gets us out of trouble a lot of the time, this is one place where you might want to consider using nullable types, because when you're generating these objects through deserialization, you don't have the compiler to hand to help you make better decisions about how your code executes. And what this means is that you can actually pull all of the null validation back into your validator. So what does it look like to validate this DTO with Koto's validation API? It looks something like this. And on first glances, this might look like a lot more code than using annotations, but we'll go through the benefits of how this works. So first off, this works on the basis of assertions. So it's kind of a similar concept to writing unit tests, where you get an object into a particular state, and then you make assertions against that state. So if we run through line by line, we can see the top line is, for all properties, they must not be null. So that's null handling for the entire object handled with a single assertion. The next one is that because obligor and obligee have exactly the same requirements, we can group those together, and then we can make the same assertions against both of them without having to duplicate any code. We'll skip currency because there's nothing particularly interesting going on with currency. The next one is amount, and the important thing to note here is that big decimal.0 isn't a constant value, so we can now validate things that aren't constants. And the other thing to point out, Koto has no dependencies on Corda whatsoever, and yet we have an assertion there which is must be valid Corda X500 name. And this is demonstrating that the validation API is completely open and extensible, so you can build your own assertions and slot them into your validator as required. There's 3 different validation modes. There's the default mode, And the way that default works is it will run through the entire object graph, collect all failed assertions, and then return at the end. You have stop on error, which will hit the first failed assertion and then throw an exception. And then you have emulation. And emulation is kind of a cool feature which pretends it's been given a subject to validate. It pretends that the subject is completely invalid and therefore returns every single assertion that your validator is going to perform. So this gives you really honest feedback about what your validator does, which can be useful if you need to unit test your validator to make sure that it's working as expected. And there are some other benefits to this as well. But what exactly does this return? Unlike most validation frameworks that either throw exceptions or just return messages, this returns an object graph. This mimics the structure of the subject under validation. So we can see that for this particular object, it was an obligation DTO. We can see all of the members that were validated. For each member, we can see its name, its type, how it was declared, whether it was nullable, and all of the assertions that were made against it, and also the conditions against these assertions. The reason that we chose to make this a graph is because it gives you a lot more flexibility with what you can do with that data. One of the things that we looked at was, in this case, we have a subset of a graph which has been serialized into a JSON structure. What we can do with this is if we emulate our validator and get back all of the requirements, we can pass that to the front end. We can bind all of this data to a form in the front end, and we can perform all of our validation on the front end. And then you have consistent validation between the front and back end. And this also has the potential to improve your network performance because you're no longer hitting the server with invalid requests. Of course, if you want to flatten this graph out into a set of messages, you can. You just get really detailed, human-readable strings. The real power of the validator comes into play when you then use this in conjunction with Koto's projection API. And projection is about turning objects of one type into objects of another type. So here, we want to turn a DTO into a state. And we can see that there are some similarities between these two objects. To do this, we could use something from the Java ecosystem. So here we have an example where we've had to refactor these objects to be compliant with mapstruct, which is an API from the Java ecosystem. And mapstruct mandates that your properties must be mutable, they must be nullable, and you have to introduce a default constructor. So this is breaking three things that we like about Kotlin, which are immutability, non-nullability, and having clear and well-defined code contracts. Alternatively, you could just write all of your mapping code by hand. So now we have extension functions that will map from one object to another. But the problem with this is really tedious work, and nobody wants to do this. And when you have lots of objects that you need to map between, this becomes a cumbersome job, and it becomes unmaintainable over time. So what's the equivalent with Koto's projection API? The best case scenario that we will get from Koto is a single line of code. That's it. And the way that this works is this works on the basis of a set of conventions, and underpinning that is a set of type converters. So it will look at your two objects, it will look at the property names and the property types and do the best job that it can to project from one object to another. You don't have to define any custom mapping code in the best case scenario. However, there are cases where the conventions won't fit your objects, and when that happens, you can, of course, break into your mapper and provide those conventions yourself. So that's it for the Koto features, and now we're going to move on to Cord, which is a framework designed to simplify and empower Corda development. One of the things that I noticed very early on as a Corda developer is that there are certain activities that you're going to want to perform fairly regularly, such as querying the vault, managing identity, and handling attachments. And there's two places where this is fairly common. So the top line is a demonstration of performing a vault query from an RPC client, and the bottom is performing exactly the same query from the service hub. But you'll notice that these statements are completely different, and that's because the APIs have been implemented differently in each place. This causes the problem that you have inconsistent code over time across your code base. It limits your ability to reuse code, and it increases the learning curve for developers because you now have to have two mindsets of what to do and where. So the first thing that we did with Cord was to implement some services over vault queries, identity management, and handling attachments. So we can see an example of this here. We're now creating a vault service from Cord, and you'll notice the only difference here is the dependency that's being passed in. You either pass it a service hub or you pass it Corda RPC ops, and from there on, all of your code is identical and consistent. The other thing to notice here is that we've elevated the contract state type from the function level to the class level, so you bind your vault services to specific contract state types when you create them, which means you don't have to pass that argument for every single function call. But what can we do to make these services more compelling for you as developers to use? One of the things I looked at was around vault queries. So this is a very simple vault query, and this came direct out of R3's documentation. And all this query is doing is looking for cache states that match currency and value predicates. There's about 11 lines of code there. It's kind of hard to reason about, and I'm sure you can imagine how quickly, if these queries ever become more complex, how hard they become to maintain and reason about. The other problem is that this is at the end of the day, it's just a query. We're just filtering something from the vault, and Kotlin developers already have a set of APIs that allow you to perform queries and traversals of collection types. So all of these keywords should look familiar to Kotlin developers, but we don't have this to hand with Corda's Vault Query API. So we did some work around this and tried to fix up the Vault service in a way that became more familiar to Kotlin developers, and also to shorten the amount of code that you have to write to write Vault queries. So going back to this example, 11 lines of code, hard to reason about, becomes unmaintainable over time, and non-standard for Kotlin developers. The equivalent now with Cord's Vault service is that. That's all the code you need to write, and you will get exactly the same set of results back. It's more familiar because you're now calling filter. You'll notice that there's a slightly unusual green color to those functions. That's because this is all now being pushed through a new DSL, which makes your Vault queries far more expressive. The other thing about the way that this works is that filter now returns a sequence, and because sequences are evaluated lazily, it means that we now have deferred execution of your queries. So we have the declaration of the query, which is inside the filter block, but the only time that the Vault will actually get hit to perform anything is when you hit that for each loop, because that's when the data is actually required. The next thing that we looked at was building transactions. We have a typical example of a transaction here, and some of the usual suspects. We've got an input state, we're then for eaching and adding a bunch of output states, we're adding a single output state, and then we have some commands to govern why we require those states and what this transaction is doing. But this code kind of doesn't read very well, and the thing that sticks out the most for me is that for each loop in the middle. It kind of breaks up the whole construction of the transaction. And over time, as your business requirements grow and your transactions change, this will just become harder and harder to reason about. But the thing with transactions is that there's a language associated with them. And we've already discussed some of that language when we're talking about inputs, outputs, and commands. And there's obviously a load of other things that you can add to transactions. So there's something that we can do about this. We can build a DSL around transactions to make it far easier to express the structure of transactions. So this transaction, when we use Cord's transaction DSL, looks like that. And now we have something that's far easier to reason about. The other thing that we did with this was to include functions that are both singular and plural. So now when you need to add a single output, you just add output. And when you need to add a bunch of outputs, you just call outputs. And that means you don't need for each loops inside your transactions anymore. But this only solves half the problem. In 6 months' time, I'm going to come back to this code. I'm going to look at these commands and these inputs and outputs, and I'm not going to have any idea why those inputs and outputs are there and which commands they relate to. And I'm going to have to go digging into those commands to try and work out why I've added those inputs and outputs. So one of the things we did with the transaction DSL was give you the ability to group your inputs and outputs by commands. This has no impact on the construction of the transaction. All this is a visual cue to you, the developer, so that in future you can come back and look at this code and you can understand better why those inputs and outputs have been added and which commands they relate to. The next thing that we looked at was flows. So we have a typical example of a flow. Specifically, this is just the call function of a flow, which is kind of the business end. And the reason I've only added the call function is because I needed to fit it on a slide. We've got 5 steps there, so it's the usual 5 things: generating a transaction, verifying, signing, gathering, and finalizing. But again, this is quite sort of almost procedural. We've had to make 5 references to a progress tracker. This is all code that we're going to have to repeat for every single flow that we're going to write. And again, flows kind of follow a language, and we've already seen some of that language here. So verifying, signing, gathering counterparty signatures, and finalizing. This is all language we use to describe how flows work. So again, we can push all of this through a DSL. So this flow with Cord's flow DSL now looks like that. So all we now need to do is forward the call block into the flow DSL, and then we build a transaction, and then we just have single-line methods that we can call to verify sign, countersign, and finalize. And you'll notice now there are no references to the progress tracker because all of the functions have overloads that allow you to pass your progress tracker steps in. Of course, every business is different, and every business has different requirements around flow logic and how you're going to build transactions. So these DSLs wouldn't be particularly useful if you couldn't extend into them and add your own logic, because what would end up happening is you'd use all of the vanilla stuff that was in these DSLs, and then you'd have to have a bunch of custom code that didn't really fit. So they are open, you can extend them. So here's an example of the flow DSL being extended with a function called negotiate with counterparties, and then we have the transaction DSL being extended with negotiations. And then we can just inject those into our flow and transaction DSL. So everything still looks consistent. Okay, and that's it for the Cord features. So the final one we're going to look at is Concerto, which is a framework designed to build business networks on Corda. Over the last few months, I've been kind of considering how the Corda network is going to grow. And the fact that there are lots of businesses now starting to construct business networks on Corda and kind of getting an idea for what those business networks are going to look like. And I've started to look at this from the perspective that business networks are going to be either decentralized and managed completely by the members of the network or managed centrally by a central authority. But I'm also starting to think of a Corda network where we aren't talking about hundreds of thousands of nodes, we're talking about hundreds of millions, potentially even billions of nodes if we get IoT and mobile devices on Corda as well. So here's a Corda network. Now I couldn't fit 1 billion nodes on this slide, so I've had to settle with 40. But we've got two business networks there which are operated by a central authority. So here we can see the formation of business networks on Corda. The next thing is we're going to have to introduce some level of interoperability between these business networks. And the reason all of these lines have been drawn differently is because if we have underlying architecture that is different per business network, you're going to need different layers of interoperability. So if you think of this on a scale of hundreds of millions of nodes, think about how many different types of interoperability you're going to need. And this is going to become a headache and something that's hard to solve. So if we solve it now, we may just save ourselves those headaches. The idea behind Concerto isn't just to provide a model for membership and relationships on business networks. It's there to provide you with seamless interoperability. And this is what we want. We want a network that just interoperates seamlessly. So there's three key concepts to Concerto. The first is membership, which provides authentication and an open identity model. I had no idea what identity was going to be required for any business network, so I didn't bother. I just left it open and said, right, this is a framework, you build your own identity per business network. The second is a relationship. A relationship is a multilateral state with an open configuration model. And this is really about defining rules for how counterparties wish to interact with each other. And finally, we have attestation. And the idea behind attestation is this is providing authorization over membership and relationship states to allow the network to agree on which membership and relationship states are valid and which they are willing to cooperate with. And the reason we did it this way was so that we could support both centralized and decentralized network models. And all of these concepts are underpinned by the workflow framework, which allows you to create, amend, and revoke memberships, relationships, and attestations. So let's take a look at what it looks like to issue membership. So this is a membership state. This is Alice's membership state, and Alice just wants to be a general user of a particular network. So she's created her membership state, she's told the network, but this really isn't particularly useful on its own. This membership state only becomes useful when somebody attests to this. So in this case, let's say it's a business network operator. The operator attests to her membership state, and this is another state which points to her membership. Then Alice is free to, of course, amend her relationship. So she's amended it here, now she wants to change her role to an admin. But Alice isn't allowed to be an admin on this network, so now we have a potential problem because we have a membership state and we have an accepted attestation. Although this actually isn't a problem because what I did with Concerto is implement this in a way where attestations point statically to specific membership versions. So all Alice actually has is an unattested membership. What needs to happen now is the network operator needs to reject that attestation. So they consume their previous one, they create a new attestation pointing to the new membership state and reject it on the grounds that Alice isn't supposed to be an admin. And so the network can continue to evolve this way until the BNO is happy with Alice's state and membership continues to evolve. Relationships work exactly the same way, except because they're multilateral, they require multiple attestations. So here we have a relationship between Alice and Bob, and this is defining the agreements for how they want to work with each other. So Alice attests, Bob attests, and now we have a relationship where they are happy to cooperate with each other under a set of rules that are configured through this relationship. Either of them are able to amend this relationship state. So now we have, again, an unattested relationship. Alice attests, Bob attests, and now we have a completely attested relationship. However, it's not completely accepted because Bob has rejected on the grounds that there is something in here that he doesn't agree with. So they will fix that, they'll make an amendment, and then this continues to evolve until they are all happy that they can work within that relationship again. So that's a really high-level overview of how membership and relationships are created in Concerto. As I'm also the author of Cordacity, what I'm going to start doing over the next few months is building some labs and samples through Cordacity so that you can see all of these features in action. Unfortunately, given that Cordacity was just a mess of badly tested code 3 months ago, that's been my entire focus over the last 3 months. I haven't had time to build any samples. In the meantime, if you do want to kind of get your head around any of this stuff, then read the tests. That's going to be the easiest way to understand everything.
Awesome. I think a round of applause, right? That's amazing, right? I think what's really cool about Cordacity, it just adds that layer of simplification now. So if you start to write Cord apps already, you'll notice that when you write your flows, there's a lot of repetition, vault queries and that sort of thing. There wasn't actually a lot of questions. There was 1 or 2 actually, but not many, purely because I don't think anyone's had time to play with it just yet. But there was one about big data or large amounts of data on the vault queries. So you talked about in Cord how you simplify vault queries essentially. So have you tested against large volumes of data?
No, not specifically large volumes of data, though. We have tried to make it quite configurable. So the default now, when you're calling things like the filter function, it will pass in a page spec that has a maximum page size, which is just over 2 billion results, which obviously isn't going to be very efficient. But what you can do as part of the query DSL, you can pass in your page spec, so you can get sequences back that are based on your page spec size. So there are ways to work around large data sets.
Great, yeah, I think that was like the following question was about paging and stuff. So another question about Concerto is, what is the plan around membership discovery within Concerto?
So around membership discovery, that's kind of a difficult thing, and one of the things I've been trying to rationalize recently is what should people be able to discover about memberships on particular networks. And if I don't belong to a network and I say to somebody else that does belong to a network, do you belong to this network? Should you be able to get back everything about their membership state, or should it just be, yes, I belong to this network? And I think it's going to be the latter, because that's the safest way. And then what would happen is you would then enter into a negotiation where you would swap membership states. So you're asking them for all of their membership details so that you can do things like KYC checks, but you're also giving them your membership to that network as well. So that you can kind of then begin to collaborate. So yes, there is still a little bit of work to do around membership discovery, but that's all kind of ticking over in my head at the moment.
I'll take it's probably one more question. This is, I think, more crucial to some of our product team that are sat in the audience. Of some of the stuff you developed in Cordacity, would you like to see any of that in Corda Core as de facto standard?
I don't see why not.
Cool.
Yeah.
I'll take that as the end of questions now. So, yeah, that's it. Round of applause for Matt.
Cool. Thanks very much.